Hello everyone, my name is Salvation. Today I'm going to discuss about the optimization of instrument condition for the analysis of mercury, arsenic, antimony and selenium by atomic absorption spectroscopy. Hydride generation atomic absorption spectroscopy and co-vapor atomic absorption spectroscopy are both chemical vapor generation techniques, which are the most powerful tools to determine the trace matter in a variety of metrics. Hydride generation is used to separate the analyte from the matrix by reducing the hydrogen to the volatile covalent hydride using sodium boron hydride NaBH form. The hydride will decompose in a heated quartz tube, and to obtain accurate result, sample preparation, which is a digestion procedure, is required. There are three processes in the hydride generation AAS. First, hydride generation occurs, and with the help of reducing agent, the sample solution release element of interest. Then, we will proceed with the hydride collection, which is an optional step. Next, optimization is occur when the released hydride transport to the atomizer by the flow of an inert gas. There are few factors that will affect the sensitivity of hydride generation AAS, which are the concentration of acid and reducing agent, the type of the reducing agent, the flow rate of carrier gas, reducing agent and the acid, and the delay time of the sample. For determination of mercury, there are one specific technique for it, which is co-vapor atomic absorption spectroscopy. In this method, we will use stannous chloride SnCl2 that act as a reducing agent to convert the ionic metal ion of Hg2+ to Hg. This will produce higher analytical absorbance signal. Mercury with high vapor pressure is liberated and entrained in an argon inert gas after passing through the liquid gas separator. Then, the mercury vapor is transferred into the optical path of spectrophotometer, where mercury absorbs light of a specific wavelength at room temperature. To obtain high sensitive result, there are few factors that we have to consider, which are the concentration of reducing agent, the flow rate of reducing agent, the flow rate of sample and carrier gas, and the delay time. Now, I'm going to explain how the factor affect the sensitivity of apparatus and what is the optimum condition. First of all, the concentration of reducing agent affect the hydride generation process, which convert the lower oxidation state of the element to a more stable higher oxidation state. For both arsenic and antimony, they use the same reducing agent, which is sodium boron hydride NaBH4. 0.6% weight per volume of NaBH4 in 0.5% weight per volume of sodium hydroxide NaOH is used to convert the arsenic from As5+ to As3+, and convert the antimony from Sb5+ to Sb3+. The reducing agent of selenium is also NaBH4, but with 0.1% weight per volume in 0.5% weight per volume of sodium hydroxide NaOH. It helped to reduce the selenium from Se6+ to Se4+. In mercury, the optimal reducing agent was SnCl2 with 25% of weight per volume in 20% volume per volume of hydrochloric acid. It will help to reduce the mercury from Hg2+ to Hg. We can observe the high concentration of reducing agent is used in antimony and mercury to achieve better signal intensity. However, for arsenic and selenium, greater signal noise was produced with increasing concentration of sodium boron hydride. Next, acid condition is also one of the factors that will affect the concentration of generating hydride. Higher concentration of acid will make the hydride generation process occur more rapidly. For antimony and selenium, 10 molar of HCl is most optimum, and 5 molar of HCl is suitable for the arsenic. And for the mercury, deionized water is enough for it. Next, we come to the flow rate of reducing agent, acid, and the sample. It has a big impact on the sensitivity. To obtain high signal intensity, higher flow rate is required. However, if the flow rate is too high, the vapor will be concentrated but unstable. The optimal flow rate for reducing agent and acid for arsenic, antimony, selenium and mercury was 0.96 ml per minute through the vapor generation accessory 77. And for arsenic, antimony and selenium, the maximum signal obtained at the approximate 7 to 7.05 ml per minute of the flow rate, whereas to obtain maximum signal of mercury, approximately 6.5 and 6.7 ml per minute of flow rate is used. Besides that, argon used, which is a carrier gas, is also important in hydrogen generation and co-vapor process. The flow rate of argon should be high enough to strip the volatile hydride from the liquid mixture and carry them up to the sample cell. However, too high of flow rate may cause the hydride become dilute. Therefore, the optimal flow rate of argon in arsenic and antimony was 0.2 ml per minute, while for selenium and mercury, the flow rate was 2.0 ml per minute. Since the hydrogenation and co-vapor process use chemical reaction to produce the hydride and vapor. Therefore, the metal ions present can adhere to the surface of various tubes and cause memory effect. To remove these adhere ions, an appropriate flushing time is needed between the samples. The flushing time can be controlled by the instrument delay time. Longer delay time will help more flushing of adhere ions. For arsenic, antimony and selenium, the optimum delay time was 20 seconds, while for mercury, the delay time is longer, which is 70 seconds, to eliminate the memory effect. In conclusion, we can find that optimizing the instrument parameters is important in the hydrogen-generating atomic absorption spectroscopy and the co-vapor atomic absorption spectroscopy. This will improve the sensitivity and reliability of the result obtained. The advantage of optimizing this condition increase the production of hydride or vapor species form, thereby improving the recoveries. So, when we carry out the experiment, we have to refer to this optimal condition to obtain an accurate result. That's all from me today. Thank you.